And there are other examples of interference through refraction, and this one, in fact, we see it all the time in everyday life. It is called thin film interference. Have you ever noticed, we look at parking spaces under sunlight, you see oil drops, right? You see, poodles of oil, and if you look at a pool of oil under the illumination of the sun, you may see multicolors, right? Multiple colors. Is it because the motor oil really has all these colors in it? Not really. What you see is an interference pattern. Okay, it's an interference pattern. Let's look at how this happens. Okay, first of all, we have a film. That's a thin layer of transparent material. Okay, we call it thin film. The thickness is T. Now it's got to be thin because otherwise light reflected this way and light bounced off that way. The path difference will be too long, and again you will encounter different wave trends for the light coming from here and from there, and they're not going to have interference. Okay, so the thickness should be pretty thin. We're looking at a lot less under a millimeter. Okay, so that's something to keep in mind. Now, suppose we have three materials with indexes of refraction of N1, N2, and N3, respectively. Okay, an incident beam of light comes in, and part of the light gets reflected directly. That's path 1. Another part of light gets into the film, bounces off this surface, and it comes out again. This is called path 2. Okay. Now, of course, we can, in principle, also consider multiple reflections, that sort of thing. But assuming for simplicity, only consider these two beams. Okay. When do you see a constructive interference from this angle? That happens when these two waves are in phase. Okay, when these two waves are in phase. And what is the condition of these two waves being in phase? Well, if we do not worry about pi phase shifts upon reflection, then it's quite clear, because the second wave, okay, has to travel an extra distance from here and then going back to there, assuming that the angle of incidence here is nearly 90 degrees, almost 90 degrees. Okay, so this is roughly t, and that is roughly t. Roughly, okay, roughly. So therefore, the path difference between the two waves will be roughly 2t, right? 2t. Okay. And if 2t equals a multiple of wavelengths, okay, m lambda, what happens? You notice I used a letter m for an integer this time. I don't want to use letter n because n would confuse with the index of refraction, which also plays a role. Now you got to be careful here. This lambda here, is it lambda in the first medium, second medium, or third medium? Well, remember, every time a wave travels an extra wavelength in a certain medium, its phase changes by 2 pi. Okay, this extra distance, 2t, is traveled within the second medium, right? So this is going to be lambda 2, okay? This is going to be lambda 2. In other words, the wavelengths in the second medium. It is not the wavelengths in vacuum, if this is a thin film, not vacuum. Okay, suppose the wavelength in vacuum is called lambda, okay? Then what is the wavelength in the second medium with index refraction of n2? That would be lambda over n2, right? The wavelength is shorter because the wave travels slower, okay? So that'll be m times lambda divided by n2. Okay, so under this circumstance, the second beam travels an extra distance 2t, which is equal to a multiple of wavelengths inside the second medium. Are you going to get a bright spot or dark spot? Well, if you do not consider any pi phase shift, you are going to get a bright spot. Okay, so if the thickness satisfies this formula, then you look directly down, almost vertically down, you are going to see a bright interference between these two. Okay, and let's say this color is red. So looking down this way, you're going to see red color. Okay, you're going to see red color because red color has been amplified by construct interference. Now, do we have to consider pi phase shift? Of course we do. But are you going to end up changing this formula? Well, that depends. Okay, let's see here. this beam of light, okay, the first beam, has a reflection. Does it have a pi phase shift? What it does, if n2 is greater than n1. Okay? So if n2 is greater than n1, there will be one pi phase shift here. On the other hand, the second beam comes in here and also bounces off. There is another reflection. Is there a pi phase shift there? Okay? There would be if n2 is less than n3. Okay? So n2 is greater than n1, but n3 is also greater than n2. There will be two pi phase shifts, right? There's a pi shift here, there's another one there, so they both undergo a pi shift, therefore there is no net pi phase shift. So this works. Okay? There is no net pi phase shift. Okay, so that's a case when both of them undergo a pi phase shift. It is also possible that neither of them undergoes a pi phase shift. And that happens when n2 is less than n1 and n3 is less than n2. In either case, there is no pi phase shift. Okay, now here, n2 greater than n1, n3 greater than n2, and here is n2 less than n1 and n3 less than n2. So in general, the condition is quite simple. Either you have smallest, medium, largest, or you have largest, medium, and smallest indices of refraction. Okay, so as long as n2 is the medium value of the is the middle value of the index of refraction. Okay, it's not the largest, not the smallest. Then there is no pi phase shift. Okay, so this condition becomes the condition for maximum interference. Then 2t equals m lambda over n2 is the condition for maxima. Interference maxima, or construct interference. What about condition for minimum interference? 2t equals m plus 1/2 lambda over n2. Okay, that of course is minima. Interference minima. Alright? Now, it is also possible we can have a net pi phase shift. This happens, for example, if there is a pi shift here but not there. Okay? When does that happen? If you have one here but not there, which means n2 is greater than n1, and n2 is also greater than n3 because you don't want any pi phase shift there. So n2 is greater than n1 and n3, in other words, n2 is the largest. Okay? Or if there is no pi shift here but there is one there. Okay? This occurs if n2 is less than n1, right? And you want a pi phase shift there, which you want in which case n2 is also less than n3. You see, so in this case, n2 is the smallest one or the largest one. Okay, it's either the smallest one or the largest one. In other words, it is not the medium one. Then you are going to end up with a pi phase shift. Pi phase shift. You're going to end up with one pi phase shift. So, what does that mean? Is that the condition for maxima and minima are then reversed. Reverse max minimum condition above. Okay, so that's what happens. Alright, suppose I have a beam of monochromatic light with only one color, okay, shining upon this same film. Okay, depending on the material you use, you know, such as air, such as oil, whatever, you must use either this condition for maximum, that condition for minimum, or you may use this condition for minimum, that condition for maximum, depending on whether there's a pi phase shift or not. Okay, and assuming that we can use this condition, okay, for maximum. In other words, there is no net pi phase shift. Then if the thickness satisfies this formula, okay, T equals a multiple of wavelength divided by 2n2, the thickness, then there will be a maximum amount of reflection. In other words, minimum amount of transmission into the second medium. Okay, and then suppose the color is red again, then you look at that, you're going to see red. Now, in the case of a pool of oil, the pool of oil usually does not have same thickness. It's something like this. Okay, so the thickness varies, right, from position to position. All right. Suppose I illuminate with a monochromatic beam of light. Then what happens? Say red light. Okay. Then for certain thickness values, you are going to see bright reflection. Other thickness, you don't see much reflection. And these thicknesses must satisfy this formula. T must be equal to a multiple of lambda over 2n2. Suppose at this particular thickness, that condition is satisfied, so it looks bright. Okay, and next one that satisfies this for different m value is here. And next one is here, 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 and so on. So what are you going to see as far as interference pattern is concerned? You're going to see ring-shaped structures like this. Okay, you're going to see red rings like this. Alright, so that is when you illuminate with monochromatic light. Now, sunlight is not monochromatic. It's got all kinds of frequencies. Okay, all kinds of colors. So each color will have its own set of maxima and minima. Minima you cannot see. Maxima you can. Let's say the red color of the sun give you these rings. What about the yellow color? Well, the yellow color has a different value for lambda, and therefore it's got its own maxima and minima location. So the yellow color may give you maxima here, here, and here, and then of course you got other colors such as such as the green one. Because the green one may give you yet another location for maximum and minimum. This is why the reflection will have multiple colors. Okay, that's the idea, even though the oil itself doesn't have all this color. It's a matter of interference maxima. Okay, now I'm assuming these are concentric circular rings if the shape of the oil is rotationally symmetrical about this axis. Usually that's not the case. So the poodle that you see, the reflection that you see doesn't have really circular shape because, again, this contour is not all that regular. Okay, but that's the idea. Can we apply thin film interference to our advantage? Well, it depends on what we need to do. Suppose you have a lens, okay, a camera lens. Now, the idea is you want light to go through the lens easily, okay? You don't want light to get reflected off of the lens, right? You want lens to go through. And then what you do is you will coat the lens, the exterior surface of the lens, with a layer of thin film of a certain thickness, okay, of a certain thickness. And the idea with this coating is that with this coating, light can easily go through. In other words, you want to minimize reflection, therefore maximizing transmission of the light into the lens. Okay, and so suppose this is air, this is the film, and this is glass. Okay, glass of which the lens is made of. And let's say for simplicity, N2 is midway between N1 and N3. In other words, it's greater than N1, which is for air, but less than N3, which is for glass. Okay, so in this case, there will be two pi phase shifts, one here and one there, right? And therefore, the condition for maxima would be equal to this, and the condition for minima would be equal to that. Okay, now which condition do you want? Do you want reflection to be maxima or minima? Of course, you want minimum, right? Because you want all the light to go through. You don't want light to get reflected. So you want to choose the thickness of the film so that satisfies this formula. Okay, so that reflection is a minimum and therefore transmission is a maximum. This m is any integer, 0, 1, 2, 3, and so on. Okay, so the thinnest film you can think of is when you set m equal to 0. M equals 0, so T would be equal to lambda over 2 times 2 times N2. Okay, N2 is the index refraction of the film. So we take lambda over 4 N2. That's what it is. Okay, Let's say n2 is say 1.25. I'm just making up a number. Okay, so 4n2 would be 5, right? Lambda over 5. Lambda over 5. Now, lambda has a certain range. That's the problem. Lambda has a certain range. For visible light, it's not a single wavelength. But we can use the median value of lambda for visible light, which is, which is about 550 nanometers. Okay, yellow-green light. So you take 550 nanometers divided by 5, what do you get? You get a film of thickness about 110 nanometers. Okay, about 110 nanometers. This is the thickness of the film you must coat on in order for the light with a medium frequency in a visible light spectrum to easily go through, minimizing its reflection. Okay, so that means if you shine a beam of visible light with all kinds of frequencies towards the lens, a lot of this will get transmitted, very little will get reflected. This is especially true for the medium frequency or medium wavelengths. The yellow-green color will be roughly 100% going through and 0 going out. Okay, so that's interesting. What if you take a look at this lens? Okay, you hold the lens in your hand, in front of you, hold the camera in front of you, and you look towards that lens. What do you see? Well, in the reflection, you don't see yellow-green because it's mostly 100% transmission, right? Okay, so the white light is now missing the yellow-green ingredient. So as a result, its complementary color will show through. In other words, you look at the lens appears to be what? Reddish, right? It appears to have a little bit of reddish and purple tint. And why is that? It's not because the lens itself has this color, okay? It is because the reflection is now unbalanced in colors. It's missing the yellow-green color, okay? And that is the way we want it. We want the most prominent light from the sun, which is yellow-green, to go through, maximizing the efficiency of the lens.